Learning Algebra 2. This is 3.3 and 3.5 of 3 Apex Semester 2, Algebra 2. So we're talking about exponential functions. The base of exponential functions determines if its graph increases or decreases. But there's some values that can be and some values that the base cannot be. So that the base can be are positive numbers and real numbers. So values that the base absolutely cannot be are negative, imaginary, the number 0, or the number, because that makes these functions not be exponential functions. Okay, so let's talk a little bit more about some exponential functions and their graph. So you have an increase graph when b is greater than 0, and your increasing graph is going to start at the left and it's going to go up towards the right. Okay, then you have a decreasing graph, and that's when your b is between 0 and 1. Okay, so it's going to be a decimal, a positive decimal. Okay, and your graph is going from high to the left and going to a lower y value at the right. There's some features that all functions have. So this is the same function. The only difference is there's an a. So it means it's a vertical stretch. Okay? So remember that anything on the outside of a function, not with the x, is a vertical stretch or compression. Okay? We can do the same things with these with all of our parent functions. We can stretch it, we can reflect it, we can move it horizontally or vertically. Okay? So the shape of both of these are curved. The b value, if it increases, is greater than 0. And on both of these, the b value is between 0 and 1 if you're decreasing. The difference here is the y-intercept. So the y-intercept on this function, the y-intercept here is 0a. You don't have to remember both, because if this is just b of x, then your a value is a 1. So if you just remember that it's always 0a, that will help you out. A value on another point on the curve is the point 1 and b. And the same thing, you can just remember this one, 1, and it's AB, because in this case, your A is just 1. Okay? So there's no point in remembering a whole bunch of different things. You always have a horizontal asymptote for these parent functions, okay? So without shifting them, at the axis. Your domain is always all real numbers. It goes all the way from the left and all the way to the right. Oh, so see, it starts all the way to the left and all the way to the right. Okay, and that's on both of these. And your range is always all positive numbers, or y is greater than 0. Okay? So those things don't change. So really, I would just focus on this column right here. Just remember, if your a is a 1, then that's going to make that a 1, and that's going to make that just your b value. Okay? Otherwise, everything is exactly the same. So that's for exponential functions. But log functions are the inverse of an exponential function. Okay? So they actually end each other. So inverse functions have the notation. So you have your original function f of x, and then you have your inverse function, and you notice it's f to the negative 1 of x. Inverse functions are actually reflections over the line y equals x. So keep in mind that's y equals mx plus b, okay, where your b value is 0 and your slope is 1. So it's just going to be y equals x, and if you graph that, it starts at 0, 0 with a slope of 1 over 1, okay, and it just goes straight down through there. So let's go ahead and look at our inputs and outputs for logarithmic functions. okay, and exponential functions. So when we're talking about an exponential function, our input value is going to be x, and our output value is going to be y. B is going to be the base for both of these. Okay? But remember, a logarithmic is the inverse of an exponential function, which means that your x and your y flip places. So from geometry, when we had a reflection, so a reflection over the line y equals x, we went from xy to yx. So here our input is going to be our y value and our output is going to be our x value. So those y's and x's just switch places. Okay? So the question that each of these asks for an exponential function is, what do you get when you multiply b, the base, by itself x times? Okay? The question for a logarithmic function is, how many times do you need to multiply b by itself to get y? So in other words, we're looking for what that exponent value is. Okay? So let's take a look at right here. So it gives you the line y equals x. And it's telling us, so to graph a logarithmic function, flip the graph of an exponential function over the line y equals x. Okay? So here is our logarithmic function, and it's exponential growth. Okay, sorry, not logarithmic. This is our exponential function. So it is the function f of x equals b to the x power. Okay? And if we, so here, let's see. So we have the point 0, 1 here. So remember, when we reflect over the y equals x line, our y and our x values switch places. Here we have the point 1, 0. And we could do that with several more points here. So this would be approximately 2, 5. Okay, so we would graph another point here at 5 and about 2. Okay? So that's how you would know how you graph this thing on the other side. Okay, so this one right here is going to be our log function. So it's log base b x. So there's different parts of a logarithmic function. We're going to come back up here for a second. So right here, this is the exponent. This is the base. And this y value is called the argument. You won't hear us use that term a whole lot, but just so that you know that there are names for these. Okay. How do we know that all three of these graphs are functions? Well, we know that they're all functions because they all pass the vertical and horizontal line tests. So remember, this looks like it's staying straight, but it's not. It's actually getting closer and closer and closer to 0. Okay? And this one too, it's actually getting closer and closer and closer to 0. Okay? So they pass the horizontal and vertical line tests, or they are called 1 to 1. Remember, they have to be 1 to 1. So let's talk about what a logarithm actually is. So a logarithm is an inverse operation that undoes raising a base to an exponent. A logarithm is the exponent to which a specific base is raised to obtain a given value. It is the inverse of the exponential function. So yes, you've always learned that, b to the x power can be done by taking the x root of b. But sometimes that's not possible because of the values you have, or because you don't have this exponent. Okay? So that's where logs come in. So bx to the a becomes log base b, a equals x. Okay, so what happens, and this is really important, you're going to have to remember this, those two things switch places, so you see they've switched places, and then your log b looks like that now. So let's go ahead and write each exponential as a log. We're not going to do anything to solve any of these, we're just going to rewrite it. Okay, so my base is going to be 2, so log base 2, and my exponent and my argument change places. So it becomes log base 2 of 64 equals 6. Okay, so whenever you finish this, your exponent should always be by itself. Okay, so this is always my exponent, always winds up by itself when I'm rewriting this as a log. Okay, so let's rewrite this one. Log base 4 equals 1. log base 5 of 1 equals 0. Log base 3 of 1 over 9 equals negative 2. That's all we're doing. We're just rewriting it. Okay? And in each case, you can see that my exponent is all by itself on the other sides of the equal sign. Okay? So my exponent and my argument are the only two things that trade places. Okay? My base stays where it's at. It just gets written as a subscript. Okay? So a subscript is where you have something down here, a small number or letter, okay, versus a superscript, which is up here, up top. Okay. All right, let's do some more of these. Why don't you pause this and try it, and then take a look and see if you got the same thing as me. So I get log base 9 of 81 equals 2, log base 3 of 27 equals 3, and log base 2 1 over 8 equals negative 3. And now we're going to do the same thing, but we're just going to go backwards. Now we're going to rewrite each logarithm as an exponent. So now our exponent, okay, and our argument are still just going to change places, and our log is going to go away. So we're going to have 10 squared equals 100. And you notice that 10 squared does equal 100. Okay, so now we're just rewriting it as a logarithm. So these two change places, and my log goes away. So 5 to the first power equals 5. Okay? If you put 5 to the 5th equals 1 here, you know that that's not right because 5 to the 5th is 25. Okay, so it's kind of a check. You can kind of check yourself there. So my 1 and 0 trade places, so I get 12 to the 0 equals 1. Well, anything to the 0 power does equal 1. Okay, go ahead and try these, and pause it and try those, and then take a look and see if you got the same thing as me. Okay, so when I do this, I get 10 to the first equals 10. I get 12 squared equals 144. And I get 8 to the negative 3 equals 1. Oh, I lied. 1/2 to the negative 3 equals 8. Okay. So next thing we're going to talk about is called the common log. Common log is a log just like these ones. You notice they all have different bases. The difference is a common log always has a base. So anytime you see the word log written without this subscript here, it means that it's really got a 10 there. Okay, so we're going to rewrite each of these as an exponential function and then solve them. So here, I'm just going to set it equal to x because that's my exponent. So now I'm going to rewrite it. Well, it says log, there's no base, so I know my base is 10. 10 to the x equals 100. That means x has to equal 2 because 10 squared is 100. Okay, so anytime we're going to start looking at, first things first, can we write it as an exponential function? All right, so x, okay, so there's a log, there's nothing, 10 to the x equals 1,000, means x has to equal 3. Same thing here, equals x, so the x equals 1. Okay, so that means I'm going to have a 0. Okay, x has to equal 0. Anything to the 0 power equals 1. Okay, here this one's going to be just a little bit more difficult. Okay, so we have equals x, so 10 to the x equals 1 over 100. Well, remember, anytime we have a fraction here, that means that our exponent has to be negative. Okay, so I can rewrite this as 1 over 10 to the positive x equals 1 over 100. It means that x has to equal positive 2, so that's 1 over 10 squared. Okay, but now let's rewrite it and find out what just x is. So that's 10 to the negative 2. So x here is going to equal negative 2. So it's a little bit more complicated with those, but it's still doable. Okay, so just remember, if there's a fraction, okay, if it equals a fraction, then that means your exponent here is going to have to be negative, which means to solve it, we're going to have to move it down to the bottom. Okay. We also have something called e to the x. Okay, so we talked about e yesterday and how it's a real number, and that it's approximate value is what, 2.718. Okay? Well, its inverse is the natural log. It's ln of x instead of log. Okay? It's just called the natural log. Okay? Well, these two things, anytime you have inverses, they undo each other. So these are actually going to undo each other. Okay? So here, the ln and the e, when they're side by side like that, undo each other. Okay? They're opposite operations. They're inverse. So when I simplify, I'm just left with negative 2x. Okay? So if the ln is first, then the e is not going to be in the exponent spot. If the e is first, then the ln will be in the exponent spot, but they still cancel each other out. Okay? E is always raised to a power, okay? Whereas ln is not. Okay? Natural log. Okay, so e to the natural log of x minus 1, the e and natural log cancel, and I'm just left with x minus 1. Okay, so this one right here, we're going to talk about this in 3.6. I don't know why we don't do it before then, but here this really goes after this x as an exponent. So really this is e natural log x to the 5th. So now that e and natural log will cancel, and we're left with just x to the 5th. Okay, this natural log and e are going to cancel, and I'm left with 0.15x. Okay, and here I have another number in front, so it has to become an exponent. So I'm left with e to the natural log of x plus 1 to the 3rd power. E and natural log cancel, and I'm left with x plus 1 to the 3rd power. So that's it for 3.3. Well, I say it's 3.3. It's actually 3.4. We skipped 3.3. So for 3.4 and 3.5, and you guys have a great day.